We've been acquainted with this unit tangent vector for a curve, but now we want to introduce a second unit vector that can be applied across the whole curve. And this is the idea of a normal vector. So if we have some sort of smooth curve C, it might be useful to construct a vector that's actually orthogonal to that tangent vector. So it kind of, it's always just riding as the tangent vector is moving, this thing stays orthogonal. Now, why would we want to do this? There's a couple of good reasons for it. But one big one that we won't cover really in this in this course is the idea of what's called a binormal vector. And that's constructed by taking the tangent vector and the normal vector and taking their cross product. So what you can do is you have a tangent, a normal, and a binormal vector, and now you have a unit vector, and the binormal vector you can get it's guaranteed to be a unit vector because these generating vectors are already orthogonal and they already have length 1. So the definition of the cross product gets you a unit vector there. But that now creates, think like a coordinate frame. So as you're going through, you now have a coordinate frame that matches the object that you're dealing with, which is very valuable when you're doing computations on like a flying object that's flying through space, because you're always looking down your own barrel. So the coordinate frame is moving, and there's a lot of really useful things in simulations or really even in real world scenarios that use that sort of information. But anyway, the task at hand, the way that we construct this unit normal vector is by taking the derivative of the unit tangent vector and then dividing that by its magnitude. And that's really all you have to do to get the unit normal, though I will say it takes a lot to compute, because to get the unit tangent vector, you have to take the derivative of the position vector and then divide by its magnitude, and then you have to take this derivative and divide by its magnitude. So getting this vector is not necessarily trivial. But you might ask yourself, why is it just as easy as taking a derivative? Why does the derivative just happen to work? Well, and the answer comes back to those properties of derivatives of vector valued functions. Remember, there was a property, it was a seventh property we discussed, that said if the dot product of two vectors is the dot product of a vector with itself is a constant. So basically, if the vector has a constant magnitude, then the vector and its derivative are orthogonal. And we can prove that using, it actually follows pretty straightforwardly by taking sort of the derivative of both sides. You would get 0, and the derivative of the dot product would use the product rule, and you'd end up with a 2 here when you added them together, and then dividing both sides by 2 gets you that. So it follows pretty straightforwardly. But remember, the unit tangent is a unit vector, so its magnitude is always 1. So that tells me that the derivative of the unit tangent vector is always orthogonal to the unit tangent vector itself. So then what we do is we just take that and divide it by its magnitude, so we always can scale up to have a unit vector. And that's really all it takes to get that unit normal.